We are studying a few new and emerging versions of TCP that are performing congestion control in their own way. One of them is data center TCP. And one of the concerns in data centers is to have very, very large throughput for most flows while having very small response time for the interactive flows, which is contradictory with the requirement to have large buffers. So you want buffers that are large enough to avoid dropping packets because of when you have many large flows that are competing, but you want to have them small to have small delay for interactive flows. And we have seen that there is a method to achieve that, which is ECN. So data center TCP is achieving ECN, but the authors of data center TCP, which is widely deployed today, found that this is not sufficient, and the main reason is the sawtooth behavior of TCP, which increases its rate until it finds a loss or an ECN mark, then reduces by 1/2, then increases it. So if you do that for a very large flow, then you have large oscillations, and the average rate is 75% of the peak rate, which is the rate that you would like to be close to, because you oscillate between 50% and close to 100%. So that's the main thing that data center TCP aims at correcting, and they do it essentially by this modification, the decrease factor. Remember that TCP does multiplicative decrease in the form of multiplying the congestion window by beta whenever a loss is detected. And this beta in standard new Reno or Reno TCP is 0.5. In data center TCP, it is given by this formula. P is something new that data center TCP host needs to do, which is to estimate the proportion of marked packets. Data center TCP uses ECN. The normal TCP does not estimate the loss probability or the marking probability. It just reacts to it. Whenever there is a loss or a marked packet, it reduces the rate, otherwise it increases. Here we do things a bit differently, which is typically interesting because we have very small round-trip times, less than a millisecond, order of a few tens or 100 microseconds, but we also have huge throughput, so that within one round-trip time, you can still have a large number of packets. So instead of reacting individually to every loss, you can estimate over one round-trip time what is the proportion of marked packets. This is what data center TCP does. And then having estimated P, it sets the decrease factor by 1 minus P over 2. Which means that if P is equal to 100%, if within one round-trip time you've lost or marked all the packets, you will decrease by 50%. And if P is very small, if you've lost 1 out of 100 packets, there will be a very small decrease here. Question?
Yeah, in a data center, you kind of own all the routers.
Yes.
So why would you not do something smarter? Because you kind of know the rate at each time. So maybe you can just control so that you can just send at a rate that's maximum all the time.
So why don't you do something smarter? Well, data center TCP is assumed to be the smartest thing done today in data centers. So perhaps you have a new idea and you should do a startup to sell it if it works. But it's not so easy to estimate the rate. I mean, the flows come and go. So, and there are hundreds of thousands of flows. So you want to estimate for each of the flow what is the rate. That would be considerably complicated machinery. It exists in cellular networks. This is how access cellular networks operate. So they estimate for every flow what is the rate that it should get based on some kind of proportional fairness. And then the signaling protocol of 5G networks, for example, will instruct the device to send what is the rate exactly. But those are expensive networks where on a given cell there is not 100,000 users, but probably much smaller numbers, and where you pay a lot for that. Here in data center TCP, we're really discussing massive things. You want to handle huge number of flows on huge number of routers also. So they do it this way, implicit computation of the rate by this adaptation. This requires also modification on how routers mark ECN packets. Routers in normal ECN routers, they mark the packets such that, sorry, not the routers, how the receiver echoes the marked packet. In standard ECN, you expect to have one reduction of the window per round trip time, so that when you perceive a loss at a destination, you mark the echo until you have an acknowledgement that the window has been reduced. So the number of echoed marked in TCP headers is not equal to the number of marked packets. This is modified in data if you use data center TCP, so that you do not do that. You try to do exactly the proportion of marked echoes equal to the proportion of packets that have been marked by the routers. If you do this, are there any side effects? That's the question of this poll. Let me close the poll in a few seconds. And the majority finds that the correct answer is B. DCTCP, data center TCP, gets much more throughput, and this is right. Why is it so? Well, because the decrease, everything is the same except for cubic and for data center TCP, except the decrease is much milder for data center TCP. Whenever there is a mark perceived by the cubic source, it reduces the packet, the window by half, whereas data center TCP will do it only in the very extreme cases. So they are competing unfairly. The increase is the same. The decrease is, in general, much larger for cubic, so cubic will get much less. So what does that mean? Well, it means there is a problem if you deploy data center TCP in conjunction with other versions of TCP, which means you cannot deploy it in the open world. You cannot assume that Google or Microsoft will deploy it for all the traffic with them, because they would simply push out the rest of the internet. Principally, should not do that. We will see that some don't hesitate to do it, but in principle, you should not. And if you are inside a data center, if you have some applications that don't use data center TCP, but other versions, for whatever reason, sometimes it's difficult to make sure everything is exactly using the version of TCP you want, then what can you do? One thing you can do is separate the data center TCP flows from the other flows. What can be the other flows? What is the method for doing that? Well, this is another dimension in congestion control that we have not used or seen now, but is done a lot. That's separation of flows or classes of flows. So far, we have discussed the public internet, which is, roughly speaking, putting all flows into the same category. So all flows are competing for all resources everywhere. And the goal of congestion control is to devise some efficient, Pareto efficient, and fair sharing mechanism. This corresponds to what is called network neutrality, that the expectation that the internet does a fair treatment of all flows. There is a lot of pressure in many places, and the current American administration is trying to modify in the US that regulation and allow operators to be non-neutral. Non-neutral would mean, for example, that data providers, the data providers are YouTube, other similar Google, Apple, etc., iTunes, that those data providers will get a treatment that depends on how much they pay. So breaking network neutrality is possible if you have a way to separate the flows, and this is possible with some form of queuing disciplines in the routers. Implicitly, the queuing discipline we have assumed in everything we saw was FIFO. When packets come in into a buffer, They are served in the order that they arrive. End of the story. If you want to separate flows, you can do smarter queuing disciplines. This can be done, as I said, in networks that don't want to be neutral. This is typically done in cellular networks. If you buy a Swisscom subscription, the price of the subscription will simply reflect the class of traffic in which you are. So if you have a cheap subscription, you will be in a class of traffic where there will be much more congestion than in another one. So how does it work? We will not go through the details, but it is essentially based on what is called per flow queuing, and the main element is called a scheduler. A scheduler is something that, for example, illustrated here. I'm showing here a router that has an output port, and on this output port, instead of having one queue, it has two. There are two classes of traffic, the red and the blue. Now, physically, there's only one queue. There's only one network interface card with one buffer, but logically, the packets on the queue are treated as if they belong to two different sets, so which we represent here by two queues. And then you have a scheduler here. So how does a scheduler work? For example, in this case, the link is at 10 megabit per second. This is a highly academic example. In reality, the rates are usually much larger today. But let's go with those numbers. The link is at 10 megabit per second. And I want to guarantee to the red 2.5 megabit per second and to the blue 7.5 megabit per second. So a simple way to do that in average would be to do, for example, a weighted round-robin scheduler that would serve one packet of this, then 3 packets of that, then 1 packet of this, and 3 packets of that, for example. That would be a simple way to do it. If we want to do that in more exact terms, we have what is called deficit round robin, where you give a quantum here and a quantum there. And if the quantum of the blue is 3 times larger than the red, it will get 3 times larger rate. And the quantum would mean I serve packets of the queue until I have exhausted a certain quantity called the quantum. Then when this is exhausted, I look if there is something to serve in the other queue. And if there is, I will serve 3 times more quantity, etc. So that's an example of a scheduler. There are many practical issues with schedulers. There are lots of schedulers, and they differ primarily by their implementation complexity. Here I'm showing 2 classes. If I have 1,000 classes, then you have implementation issues that start to be important. How much time does it take to screen all the different packets that are queued in all the queues to know which one I should serve now? So those are the kind of issues that different schedulers are trying to optimize. But we will not go through all those details. And let me assume that I have simply a way to classify all traffic in my network as red or blue. And I have schedulers that will guarantee this. Now, a property of those schedulers is that they are providing a guarantee, but they are flexible in the sense that you can borrow from other classes if there is spare capacity. It means that if the red traffic is not existent, if the red traffic is 0, then what will the scheduler do? It will serve the blue for 3 packets. Then it will see if there is something available to serve in the red, and if there is nothing, it will continue serving the blue. So in fact, it will give 100% of the rate to the blue traffic, but it will make sure that the red is always guaranteed 25% of the rate if there is something to serve. So it isolates the flows, but does not strictly separate the capacity. Strictly separating the capacity is a mechanism that is what you obtain when you use what is called time division or frequency division multiplexing access, where you have a static separation of the time, for example. Some protocols like Bluetooth or Zigbee use that kind of thing, so they would separate strictly the time by saying every millisecond between 0 and 2.5, I look only at the red, and between 2.5 and 10, I look only at the blue. And if nothing happens to the red, well, it's not used for the blue. This is what TDMA does. GSM networks work in this mode. But here we have smarter things. So in the lab, we have this in Linux machines in the functions called traffic control, TC, for example, that implement those kinds of things here. So this would be a way to, for example, have data center TCP and regular TCP to make, for example, if you want to guarantee some part of your data center capacity for your internal flows, and if the flows that come from the outside, which you can't control, which version of TCP they're using, you want to guarantee them some fraction of the resources, this is what you could do. Another classical example, which is the one shown on this figure, is if you have non-congestion controlled applications. Here I'm showing sensor applications that send traffic at a given fixed rate. This can be a video camera, this can be a temperature sensor, this can be any equipment that is measuring the physical state of some process, like in electrical grid phasor measurement units. So they typically send at a given rate, which is given by the hardware, and whenever they have measured something, they send it. And those applications, as we have discussed very often, don't use TCP. If you do that, then a good reason for using that class-based queuing is to make sure that you isolate the non-congestion control from the congestion control. Isolating them is important because you rely on the operation here. If there is no congestion control, then we have seen that in theory the system can collapse. Now hopefully here it won't collapse. If you want it to not collapse, what should you do? You are designing those sensors. You have those sensors, you know at which rate they send, and you have to make sure your network operates. Well, you should count, you should plan your network, you should do what is called traffic engineering. You should count how many sources there are and make sure that on every link there is enough capacity to handle them at the max speed that they can generate. So if the two sensors are sending at 1 megabit per second each, then here I've guaranteed 2.5 megabit per second to each of the two flows, so that will be okay. I need at least 2 megabit per second, plus, as a good engineer, 20% margin. That gives me 2.4, 2.5 megabit per second. So that is okay. That is called traffic engineering. You compute the max rate of all the flows, and you make sure that there will never be congestion anywhere. So you will not need congestion control because the sources are never sending more than the capacity of the part of the network that is allocated to them. So you could do this, and that could be sufficient. And if you could do it without class-based queuing, because you say I have two streams at 1 megabit per second, my links are at 10 megabits per second, so in the worst case, I will have 2 megabits per second taken away for the others, and the others will share it using TCP congestion control. However, if you do this, you might still not be fully satisfied. You may still be interested in separating them by having class-based queuing. What could be a motivation for separating? Well, it's the opposite of what is happening in this class. Nobody's speaking, but you can have the opposite, which is called the babbling idiot. If you have a machine that, for whatever reason, emits traffic uninterruptedly. You can say, well, that's stupid, that will never happen. Well, we know with software systems, stupid things happen. It's called bugs, and malicious things even worse. So it can be that the hardware is stuck and is constantly repeating the same frame, for example. So instead of sending the same frame every 20 milliseconds, it sends it continuously. And therefore, instead of sending at 1 megabit per second, it is sending at the line rate, which might be 10 megabit per second. So you might have a device that floods the network. It's a denial of service attack. And if you want to be protected against this, if you have congestion control, that would help. But if you don't have congestion control, then you want to isolate the flows. So this is the kind of settings that you find typically in networks that combine industrial applications with IT applications here. If If we have this setting with all the details I've given before, and now we focus on PC1 and PC2 that are connected here and that use TCP to transfer some information to the backup server, for example, here, which rate will they get? I close the poll. And the majority says B, which is the correct answer, at least within the approximations we can make on when we reason theoretically. We see in the lab that things are not as clean as in theory, but approximately this is what would happen, because this is the network that PC1 and PC2 will do. On the first link, there is 1 megabit per second that is taken away by the red queue. The scheduler will therefore deliver to the blue to the rest the remaining capacity. It will guarantee 7.5, but since the red is using less than its committed rate, it can use up to 9 megabit per second. So in average, this is the same as having a link at 9 megabit per second here. On the second link, there are the two red flows that are coming, and the maximum rate now is not 9, but 8 megabits per second. So for PC1 and PC2, everything is as though there would be this network with a link at 9, a link at 8, and here also a link at 8 megabit per second. So what does TCP allocate? Well, we can use the loss throughput formula, we can use the utility formula of TCP, or we can also first look what it would allocate if it uses max-min fairness or proportional fairness. But in all cases, we see that what are the constraints on the rates? The constraints on the rate are given by the 3-link, so the x1 is less than 9, x1 is also less than 8, and x1 plus x2 is less than 8. And we see that out of those 3 constraints, the first 2 ones are redundant. If this is true, the first 2 are certainly true as well. So in fact, the limiting factor, the bottleneck, there is a single bottleneck, and it is this one. So it is as if PC1 and PC2 were limited by a link at 8 megabit per second. Now if you take 2 TCP flows on one bottleneck, then they will receive throughput inversely proportional to their round trip time. Now in this academic example, the round trip times are exactly the same, so they will get the same, which is 4 megabit per second. Question?
Did we not say that TCP would be less fair with flows that use more resources? So here, the first flow goes through 3 routers, while the second one goes only through 1.
So the question is why we said that TCP is between proportional fairness and max-min fairness, and it's closer to proportional fairness, and proportional fairness has the effect of giving less to flows that use more hops. It's true, but it's a qualitative statement. Now we have to look at the details. It would be true if those links would also be bottlenecks. So if there would be TCP flows here that are able to congest this link and this link, then this would be true. In that case, PC1 would get less than PC2. But here, and this is visible in the inequalities, we see that 2 out of the 3 constraints are not binding, they are redundant. So in fact, it is as if those links did not exist. Of course, this is a highly special example. In reality, in a large network with lots of flows, it's very unlikely that you have one link that is underutilized when, if there are local flows here, they would take advantage of this to increase the rate. The last topic is what happens to UDP applications that are competing in the internet and need to be congestion controlled. So what should you do? Well, the internet took a very radical shortcut. The internet people thought, we have solved the congestion problem once for all with TCP Reno. So this is the golden standard of congestion. So whatever TCP Reno does, with all the bias and all the small side issues, it is good. And the proof is that the internet has been working for over 20 years with that, so that should be okay. So what everybody should do is not be more aggressive than TCP arena. This is called the concept of TCP friendliness. So we say that an application that is not using TCP should be TCP friendly, which means that it should not get a rate that is larger than it would obtain if it would be using exactly TCP. And there are various ways to do it. The first way, so it's typically for a UDP application. If you're a TCP application, then you use TCP congestion control. If you are a UDP application, then you can simulate exactly or implement exactly all the congestion window computations that TCP does, if the nature of the application allows it. This is done by things like QUIC that we will discuss in 2 weeks. So if you have an application that has a concept of elasticity, where it can send packets and wait for some packets before being able to send them, then you can compute a congestion window. And also, this is assuming you receive acknowledgements or ECN marks. Right? So typically, this is done not with ECN, but with losses. So such applications receive acknowledgements and then do additive increase, multiplicative increase. Another method, but this is not adapted to all applications. For example, if you're streaming interactive audio or video, you don't want to delay a packet because the window is not allowing you to do so. So you want to control directly the rate of the application. So classical methods for managing video applications is to have a rate control coupled with the coding method, with a video coding method. If the rate is small, then you code with a low resolution, both in number of pixels and in depth of the colors, for example. If you have a higher rate, then you will use a higher resolution. So typical modern coders have a large number of rates, of coding rates, that each produce a different information rate. And then you get from the congestion control module the rate at which you can send now, and then you use the coding layer that is compatible with this rate. So the impact is that the coding quality varies, which you see that if you watch videos, you see sometimes it's high definition, and sometimes, although you've clicked on the high HD box, it doesn't look HD. Well, this is because the rate that your connection is getting does not allow this level of quality. Offline applications, when you watch a YouTube video, for example, typically use TCP or the Google equivalent of TCP, which is called QUIC. So this is using the standard TCP congestion control. Interactive audio, like Skype or video, use something else, which is close to one example of this is called TFRC, TCP Friendly Rate Control. That's a method by which the application determines directly a rate, so the application is not using a window, is not simulating or implementing exactly the window mechanism of TCP. Instead, it's computing a rate. And which rate does it compute? It computes the rate given by the loss throughput formula. You may remember there is a formula that says that if I can estimate the loss probability or the ECN marking probability Q, then the throughput that my connection will get is 1 over square root of Q multiplied by other terms. So such applications implement this formula by taking as input to the formula an estimate of the packet loss, which they get with statistics reports of protocols like RTP. When you send a video to a destination, the destination is able to say how many packets were lost. So every round trip time, it sends one report back to the source saying what fraction of information has been lost, or equivalently, which one has been received. It's not like in TCP. This is not used to hack exactly because such applications are real-time constrained. If a packet is lost, it's too late. There's no way of repairing it because there is another video frame that's coming with 25 or 24 video frames per second. So there's no point repeating a lost packet. So this is just serving statistics purposes to get an input to the loss throughput formula. And then based on that and some smoothing, of course, this rate may vary dramatically. So you smooth it typically with a low-pass filter. And then the application, therefore, computes a sending rate, which is approximately what a TCP application would give. Not exactly, of course. It's not simulating it exactly like you're doing here, but in average, it's expected that it gives roughly the same. So this is what a TCP-friendly rate control, TFRC, does. Any questions so far? Last, there is a new version of TCP that is receiving a lot of traction and is widely deployed in the internet today, probably a significant fraction of the internet, I don't know exactly the numbers, but perhaps 20% or more, is using TCP-BBR, which is the newest invention of Google. It's called Bottleneck, Bandwidth, and RTT, BBR. So it's an acronym of acronym. And here it's completely radical. It's a revolutionary way to do things where in TCP we send packet until we get negative feedback and then we decrease or increase depending on the feedback we receive. And we've seen all the variants with which we can do that. Here we ignore losses. So no feedback from the network in the form of losses. The only feedback we get from the network is what is the rate we achieve. So the source is trying to send a number of packets. Then you can measure in one round-trip time how many of those packets are received at the destination. Of course, over the long run, you expect that what you receive is what you get, what you send. The difference being what is lost or what is buffered. But over the time scale of one round-trip time, if the buffers are very large, then there might be large variations. For example, when we have discussed the buffer bloat syndrome, it may be that if a network is congested and a buffer is very, very large, it may be that during one round-trip time, nothing is delivered to the application, but nothing is lost either, simply because the data is accumulating in a buffer that is getting larger and larger and larger until it gets lost. We have seen that there's a fix to that. It's called ECN. But the Google people, for some reason, they don't know or they don't want to use ECN, so they did something different. The goal being the same. The goal is to avoid inflating the buffers, which we have seen is detrimental because we add delay everywhere with no benefit to the throughput. So it's the same goal as we have with data center TCP and with ECN in general. But it's achieved by a radically different method. First, the TCP source controls the rate, not the window, which is a good thing. So there is still a congestion window, but in addition to that, there is a rate that says per smoothing interval of roughly round-trip time, how many packets can be sent by the source. We have seen that there is a subtle difference between rate and window. In average, it's the same. If you control the window over long periods of time, you are controlling the rate. So controlling the window, in average, controls the rate also. But over short periods of time, that may be different. We have seen that the reason why things like TCP fast recovery exist is that there is a difference between the two. The window may be such that you cannot send anything because you're missing an acknowledgement somewhere, so your rate is 0 for some period of time. It may be the other way around, even though in average with TCP your congestion window says how much you can send, but it can be that, for example, the window was blocked and all of a sudden you receive a missing acknowledgement. Then all of a sudden you can send perhaps 20 packets. So you can generate a burst of 20 packets at some points in time due to receiving a missing acknowledgement, which will cause large irregularities. So the rate over small periods of time may be non-smooth. So they're trying also to avoid this problem. And then the feedback you get from the network is the estimated rate, the rate of delivery, measured by the destination, and the RTT. And the striking feature, which is probably the source of all the problems of the system, is that losses are ignored. So this is a simulation taken from this source here, showing in green, the plain green line. This is the throughput obtained in megabit per second for one TCP-BBR flow. We see that there is like kind of slow start at the beginning, then it regularly sends, and we see that the rate is practically constant with periodically a small decrease followed by a very tiny increase here. But we see that in average the rate is very constant. Compared to the rate of these oscillations here is the rate of cubic, which is the standard in the internet today if you don't use BBR. So this is avoiding, like DC data center TCP, avoiding these oscillations by sending at a constant rate. So how does it work in detail? The mental model or the operational model of BBR is that the network is a single bottleneck, which might be an issue. We have seen that when we talk about Pareto efficiency, typically there are multiple bottlenecks. But here they view the network as a single bottleneck. And then a BBR TCP source estimates the RTT, the round-trip time, by taking the minimum measured RTT over the last 10 seconds. Estimating the RTT is, of course, an issue. Which RTT are we talking of? So here what they want to compute is really the round-trip time, avoiding queuing delay. Right? If the buffers are full, then the true RTT will be very large. But what they want to estimate is what is the RTT if there is no queuing, which is, of course, is impossible because you don't know whether there is queuing or not. But if you take the minimum of all the RTTs you've measured over the last 10 seconds, probably the minimum is closer to the delay you would have if there is no queuing. Right? So that's the first element. The second element, you estimate, the source estimates the bottleneck rate, which is the maximum bandwidth, called bandwidth because it's computer science, but it's really a rate, which is the maximum rate you can achieve over 10 RTTs. Right? And this is by simply looking how many ACT data have been received. And then you send data at this rate, the rate of the bottleneck. So you see how much you can, and you do how much you can. Right? With a small modulation, the modulation is this number C of t, which is essentially saying you send at this rate, C of t is 1, during a number of round-trip times, but once in a while you overshoot it and then you undershoot it. So here you say you probe bandwidth, so you try to get a bit more with the idea that you always, the same idea as additive increase, multiplicative decrease, you want to test the water and see if sending more would work. And then because the primary goal of this design is to avoid filling buffers unnecessarily, you took a risk by overshooting, which might be that you send more than the average rate that would be okay for your flow. Therefore, you want to drain the buffer, and by sending more, you may fill the buffer, which is the opposite of what you want. So you drain the buffer by sending a bit less in the next time slot. And then you send at a constant, not at a constant rate, but at the rate BR, which is the one you have observed. Right. So this is the main ingredient of BBR operation, and we see that it provokes a practically constant sending rate with once in a while a small fluctuation here. There are other details that I skip. Now the main intention is to avoid filling buffers because it estimates the bottleneck bandwidth. So if there is one flow that is trying to push itself into a buffer, with this operation, it will be able to estimate fairly accurately what is the available capacity that it can use. And it will send at this capacity only. It will not wait until the buffers overflow to detect that it is using the capacity. It is estimating directly the capacity. So in some sense, doing a bit what you were suggesting, estimate the rate and send at the rate. However, so far there's a lot of controversy about this, and at the ICMP conference last month, at the ITF this month, there were lots of people that were completely upset by the deployment by Google of BBR, essentially because it has been shown here, those are lab experiments that show what happens. On the right, we see, for example, a 10 gigabit per second link in a paper that is given as reference in the slides. And this in yellow is the performance of cubic, and in blue is the performance of BBR. So we see that BBR regularly has a small phase where it drains the buffer, but other than that, it's a fairly constant rate. So at the beginning, there's one BBR flow, then a TCP cubic flows, and we see large unfairness. The TCP cubic flow is unable to get anything of the buffer here. And in a case like this, it is because the loss rate is extremely large. So there has been reports that BBR can cause loss rates of 30–40% on some links, but BBR will ignore those. There is no reaction to loss in BBR. It will estimate how much goes through and will ignore the losses. So that's one of the issues. Gross problems, at least when the buffer sizes are not very large. Here's another example that is showing also a random, so this is all BBR flows on the same bottleneck link, and you see that some BBR flows are unlucky, some are lucky. Which essentially means that BBR is trying to estimate how much can I get by inserting myself into this link. Now, if you come at the wrong period in time, you estimate that your fair share is small, but your share is small because you have others that are already using a lot, and there is no mechanism to really force the others to give way to you. So we see that some of the flows are practically during the entire period getting very, very small throughput for a very large sustained period of time here. So stay tuned. BBR, as I said, is deployed by Google, so large majority of Google traffic is using cubic or BBR. If it's TCP, it's using BBR. And the future will tell whether they can fix the problems that BBR has today. So as a conclusion, the first conclusion is perhaps, well, congestion control, although well understood for over 30 years, continues to be a very animated landscape with lots of things happening. So this is fantastic and exciting. What do we need to remember? Well, congestion control is performed by TCP or TCP friendly applications. Too much buffer is as bad as too little buffer. ECM can be used to avoid the problems, and class-based queuing is an important mechanism that we find in networks that want to control things and separate them. Voila, that's the end of the congestion control module. And before the break, I would like to do a little thing, which is to give you feedback about the evaluation. Okay. So the first feedback is I don't congratulate you because there's not many answers. But it's better than last year, but not many answers. The feedback is very positive about the course, so thank you very much. Thank you also to all the TAs who are doing a lot of work. There are a few detailed comments that I've tried to distill here. So complaints are about the lab bugs. So we're aware of those and we try to reduce them. Someone made the remark is, why don't you debug the labs by having someone who did not design it try it as a student would do. Of course, we do that. So the bugs that you see are the bugs that come after the debugging phase, right? So we try to do that. We do that. So any lab is designed by one TA and is tested by another TA who did not take part in the design of the lab. Right? But of course, sometimes there are bugs. The bugs are more difficult for us to control because of we allow you to have your own environment. So of course, it's the Linux tools that we use, Mininet, for example, are a bit susceptible to the environment in which they are. For example, if you updated your Ubuntu every day, like you normally do, then you might have introduced a version of one piece of Mininet, for example, that will not be compatible with Mininext. And of course, you might discover that, or we might discover that with you the day of the lab. So we try hard to do our best, but it's hard to avoid all bugs. Now the quiz questions, not always well posed, and I think sometimes there are ambiguities. This is in particular from the smarter of you, or the ones of you who know particularly well one topic, so you can always argue whether it's not true that under some circumstances. So yes, you are right, sometimes they were not always well posed. This is also debugged, of course. The quiz are done by one person, by me in general, tested by one TA, and okay, we don't catch everything, but we'll try again to catch all ambiguities. We had a glitch also. One video was not online before the quiz. I think that happened only once. That was really a glitch. Normally, of course, we put the video online the same day, particularly if there's a quiz the following day. Then the video is not sharp. Yes, it's true, but you have the slides also. We're aware this is not the best and most fancy thing we could do. Next year, we'll try to do something fancier if we find tools that are convenient. The audio also, there were some complaints about the audio. I'm not really sure what that means. Is everybody hearing me well in this room? Do you hear me? Okay. So I guess this might be a bug. Well, that's the feedback we have from you. Are there any other things anybody would like to add or discuss? No, then if something else comes later, please put it on Moodle. We're happy to take any feedback. And in the meantime, we do the break and resume in 10 minutes. We now change topic. We restart and study BGP. BGP is what really runs the internet. So if your problem is to devise a network that is, say, an industrial network within a company, probably you don't care about BGP. But if you're interested in how the internet globally works, welcome, this is about BGP. BGP is called external routing, also called inter-domain routing. We have seen OSPF in the lab, a bit painfully sometimes. We will see a bit later towards the end of the course RIP and other distance vector protocols. Those are all routing protocols that work within a domain. Within a domain means there is a single entity, a single service that manages the network, in particular the weights, the costs, and that indirectly say where the traffic goes. Now, the internet is too large to be run by a single domain, even if we use the OSPF trick of having areas. An OSPF single area can be perhaps 100 routers. If you have a very large network with 1,000 routers, then probably you would have a network with 10 areas. But that would not be sufficient to run the world for two reasons. I mean, first, OSPF itself with multiple areas has a limit. And second, there is not a single entity that's running the internet. Who is running the internet? The Americans, China, ITU, United Nations. Well, no one is. It is self-organized. There are treaties and there are standard bodies. The IETF is one of them that says how a routing protocol should be or how TCP congestion control should be. There are standards for telecoms, but they just specify the technical protocols themselves. Now, how you run them, how you deploy them, how many routers you put, whether you have links at 1 gigabit or 100 gigabit, how much you charge, who connects to whom, this is not specified by anybody. That's an emerging property of business, of the interest of people to be connected with each other. So nobody is running the internet, and this is, as we will see, be reflected in the way BGP is designed. There is still BGP at the heart of everything, which is standardized, but how you set up all the attributes of BGP, there is no entity that says that. So interior routing means routing protocol that are within one domain. OSPF is the example we know well. Exterior routing is the routing protocol between domain. There is only one. There's only one exterior routing protocol. It's BGP, BGP version 4. There were other ones that existed when the internet was minuscule and nobody cared about it. Now, since the internet has become important, BGP is unchangeable. Just like it's very hard to move from IPv4 to IPv6, it would be even harder to move from BGP to something else. So there is a tomorrow which would be better than BGP, but concretely, probably tomorrow will also be BGP 4. So we have this distinction between a single BGP between all domains, and inside the domain, everybody does whatever they want. The internet is made of domains, and domains are called classically autonomous system. So in the language of BGP, a domain is called an autonomous system. It's also called an autonomous routing domain, ARD. Those are practically synonyms. There is a subtle difference. An AS is an ARD with a number. So all the domains in the world that participate in BGP require a number. A number is a 32-bit number, like an IPv4 address, but it's not an IPv4 address, it's a domain number. For example, the number of switch that serves EPFL is 559. It's originally it was 16 bits, and it was written as a decimal number. Then 16-bit quickly appeared to be too small, so it was expanded to 32 bits. Now the domain number is not in the header of IP packets, so changing this number was not such a problem as changing the IP address. Now it's extended to 32 bits and is written in dotted decimal notation with blocks of 16 bits. So 0559 means 559. Right. There are also private numbers. Sounds familiar. Whenever we invent a numbering scheme, we reserve part of it for private things. We'll see a use of it. And here are a few of the examples. The one that we're connected to is switch, which has this number. EPFL doesn't have a number. A special case where you don't need number is when you connect to the internet by a single provider, which is the case of EPFL. EPFL is going through the global internet through switch. So for the rest of the world, it's always visible through switch. So for such systems, you don't need a number. Here is how things fit together. A bit of terminology. In BGP terminology, or in networking in general, we say that a network can be a transit or a stub, essentially. Transit means, like this network, a network that can be used to carry traffic from one network to another network. And a stub is a network like this one, which is connected to only one other network. Like EPFL is a stub network. We have seen this concept in OSPF already. OSPF makes the distinction of networks in the sense of OSPF, which are Ethernet prefixes. Prefixes are stub if they are connected to just one router. And for routing, stubs can be ignored because you know if you want to go to a stub network, all you need is to go to its unique neighbor. Oops. We have a visitor. And sometimes you have also multi-homed. We'll talk about that again. We see that BGP, in principle, is used between domains. So here we have a router in this domain, a router in that one, and they're using BGP. In addition, inside the domain, even if you use BGP, you're expected to run your own routing protocol, which may be OSPF or Cisco's EIGRP, for example. The method used by BGP is path vector with policy. There are two keywords associated with BGP, so let's see what this means. Path vector is a very different routing method compared to what we have seen with link state, which is illustrated here. A path is a sequence of AS numbers. This is the first place where we see the use of having a number for AS. For example, assume AS number A has prefixes internally, N1 and N2, and it wants to make them visible to the rest of the world. And it has two BGP neighbors, B and C. So via BGP, so all those messages are BGP messages, A will inform B that it has network prefixes N1 and N2, and when B receives that, it will append, or A will add its own AS number to it. So the path to N1 seen from B is A, N1. Now B will receive this and will keep it for itself. If the policy allows B to forward this information, it will inform E by appending its own number to it. So B will say to E, I have a path to N1, which is BA-N1, and similarly to N2, and I have a path to N5, which is B-N5. Through some other paths, E will have received, for example, this path from D, DCA-N1, DCA-N1, that has come all the way here. So that now E has received two informations about the prefix N1. It knows that the prefix N1 is visible through the path AB or BA and through the path DCA. Right? This is the information that BGP will pass along. So BGP is not computing shortest path. It is simply accumulating the path where the paths are visible as a concatenation of AS numbers. Now when E receives this, it will have those two paths to N1 and N2. And one of the rules that we will repeat on BGP is that in BGP, any BGP router keeps always only one route, one path, and one route for any destination prefix. So E will choose one of the two. For example, to N1, here it has chosen BA, BA here. So it thinks this one is less good. Perhaps because E is applying a rule that says, I prefer the path that has the smallest number of ASs, the shortest path in number of ASs. Of course, counting the number of ASs might not be at all the same as the true length of the path. Perhaps those ASs are very small, there's just one or two routers in each of them. Perhaps this one is a huge one with 10,000 routers. So perhaps the path through this, when we go in detail through each of the hops, maybe this is a much longer path. But this is not visible at the scale of BGP. BGP hides the details of what is happening inside. It keeps only this view of the ASs and their interconnection. And in particular, why do we do this? Well, this is because by giving the full information about the complete path to every domain, to every AS, we leave the possibility to every AS to choose its path based on its own criteria. For example, perhaps E doesn't like C for whatever reason, because C is spying all the traffic, perhaps. Or C is not network neutral and systematically discriminates the traffic, or whatever reason. Or they don't like each other. There are countries that don't like each other. Like there are lots of examples on Earth. So by having the path here, E may decide, for example, to, as much as possible, never route through C. So E would route traffic to A this way, to D this way, but we never use C as transit. That would be an example. That's called policy routing. We'll come back to it in a minute. This is enabled by having this description of the entire path. But before we go there, a few more details on BGP. BGP is a system for interconnecting domains, and it works by having one BGP router at every side of the boundary between domains. So if D1 is connected to D3 here, domain D1 and domain D3, if they talk with if they use BGP, which is the normal case, they need to have each of them their own BGP router. And the only thing they have in common is a link between the two. This is consistent with the idea that we live in a self-organized world. D1 connects to D3. They want to share as little as possible. In particular, they try to avoid having to share a router. If you compare to OSPF, that was the opposite. In OSPF, an area border router is present in the two areas. But it makes sense for OSPF. OSPF is a single domain system. Even if there are multiple areas, it's a single domain. If you're in a single domain, there's no problem sharing, hopefully, there's no problem sharing a router between two areas. And it's even more economical. You don't want to put two routers if you could achieve the same thing with one. If you're between domains, in principle, you don't want to be forced to share. It's possible to have a common routers, and there are examples where this is possible. But in principle, the most widespread model is that there is a router on each side of the boundary. And then BGP is the protocol that is used between routers across the boundary. BGP routers talk to each other over a TCP connection. They exchange their information over a TCP connection. But different from OSPF. In OSPF, we have seen that routers talk to each other using their own reliability mechanism. They don't use TCP. They transmit a message. If the message is not ACT, they will retransmit it until it's ACT, and then they will flood, etc. Here, there is nothing like this. They use TCP here. Now, A talks to C, and through BGP, C learns about things like XN1 here. But now, C needs also a way to pass the information to other BGP routers. If a domain is large, which is quite typical, a domain has more than one BGP router. It has more than one interface to the other networks. For example, Swisscom has interfaces to other routers in Zurich, in Basel, in Geneva. So you have multiple BGP routers, and you need a way that the router C, that has learned about the outside world through BGP here, passes this information to E that will then pass it along to other routers. So you need also a protocol between BGP routers inside a domain. Now, the principle of BGP is that this protocol is also BGP. There is not an interior protocol and an exterior protocol. When you talk BGP, this is always the same BGP. So C, E, F, and D also talk to each other using BGP. More precisely, BGP makes the assumption that all BGP routers inside one domain are able to talk to each other directly. So here, this is illustrated by C has a TCP connection to D, C has a TCP connection to E, a TCP connection to F, and a TCP connection, and etc. So there is what is called a full mesh. This does not mean that the BGP routers are direct neighbors. They are not necessarily on link of each other. That would be a completely impossible requirement. If one network is in Zurich and the other in Geneva, there might be multiple internal routers in between, which is shown by this router here in the middle. The router R is on the path between C and F. So C has a BGP connection between C and F as a TCP connection that goes via router R, and in this example, router R is not a BGP router. So BGP routers are connected by means of TCP connections, typically on link when you're talking to outside neighbors. Inside a domain, there is a mesh, a BGP mesh, and they are typically not on link. Very often we will use the terminology eBGP and iBGP. E means external BGP and I means internal BGP. It means BGP used internally or BGP used externally. It's the same protocol. A few rules are different on how you use BGP, whether you use it internally or externally. Essentially, the only two rules that are different are those ones. First, a router, when C, or for example, A sends a route to C, the route X and 1, then A will add its own AS number, D1. So when you're a BGP router and you speak to somebody externally, you add your own AS number to the path, because that's the semantic of path vector. But you don't do that internally, because it's already present here. So that's only an obvious difference. A less obvious difference, but which makes a lot of sense, is you don't repeat over iBGP what you have learned over iBGP. So what does it mean? Here A has learned a route over, C has learned a route from A over eBGP, then it will pass the information to D, E, F. Now, because C passes the information to D, E, F, because we have a full mesh, the BGP mesh is full, there is no point that E repeats the route learned from C to F over iBGP, because there is a full mesh already. So this is the reason for this rule here. Let me skip this. Okay, small quiz. I close the poll. And the correct answer is A. Two BGP peers must be connected by TCP connection. That's what is called the BGP mesh. And they must not be on link of each other, as we have discussed. Now we will see that this is not necessarily always true, even. We will see that, as usual, and that's also one of the problems of the quiz, is that in practice there are always many different subtleties that may show up, but as a first mental model, we assume this. Of course, if you have a very large network with 1,000 BGP routers, having a full mesh might be perhaps not very efficient. So there are smarter ways that we will see to achieve the same as a full mesh and being more scalable. They're called confederations, for example. So we'll talk about that a bit later. But as a mental model, I think it's useful to keep this one. Here, this question is about which updates can be sent. So C, D, and C would like to send those updates. Which ones are legitimate? Okay, I close the poll. And the correct answer is D. So the first update is sent from C to A and is about the route D3, D2, X, and 1. So that's a route that C has learned from D and it's repeating to D1. That's the normal job of BGP. Domain D3 has learned a route this way and it's passing it to D1. It's legitimate if, as we can see, the domain D3 agrees to do it. You're always free as a BGP speaker to not say something. But it's legitimate according to the rules we have seen before. Now, D to E, D repeats to E the route D2X and 1. Well, this is a route that D has learned from the outside, and it's propagating into the BGP mesh. So it's not like OSPF here. In OSPF, if we would use the OSPF way of doing things, D would repeat it to some neighbors, perhaps C and F would get it from E. So we would have a gossiping protocol. That's how OSPF works. In BGP it's different. In BGP, there is a direct TCP connection, right? Because we assume that in a large network, there are a few BGP routers at the edge, At least that's one mental model. We will see that very often it's not the case. And there is a mesh inside, a mesh of routers and switches inside the domain that allow communication. So gossiping is not necessary because we assume that the IGP has done its work and that communication within the cloud works without BGP. The third one, C to E, is about D to X and 1. So this has certainly not been learned firsthand by C. If it had been learned firsthand from the outside by C, it would be prefixed by D1, not by D2. So C has learned it from D. And because C has learned it from D, C is not allowed to repeat it to E because E will receive it from D. So it would be doing unnecessary work since we assume there is a full mesh. That's an example where, at least to be consistent with the assumption, we don't want to repeat the same information several times. So BGP is using path vector routing, and the major motivation for this is to be able to do policy routing. So what is policy routing? Well, policy is about the fact that the relationship between networks is not necessarily a peer-to-peer relation. If all networks would be peers in the world, and there would be a non-for-profit collaborative system, perhaps we would not need policy routing. But the internet is organized as a large commercial entity. So the commerce means there are networks that sell service to other networks. For example, EPFL is a customer of Switch. Switch may be itself a customer of AT&T, because Switch, which is worldwide a small entity, doesn't want to build a big infrastructure to connect to everybody in the world. So Switch will connect through larger providers to the rest of the world. Of course, AT&T, if they allow Switch to connect to them, they will charge Switch for that. Just like we are charged by Swisscom or others for having access to the internet. So there is customer-provider relationship, and sometimes there are peer relationships. Those are the two main forms of relationships. For example, AT&T and US Sprint, or Swisscom and Sunrise are peers. When they work together, probably none of them is a customer of the other. In such conditions, then there might be reasons for not allowing some paths. Here is an example. Here are several examples. So the example I'm using is assuming that I have three ISPs, one that's local to the US or Canada, one that's local to Europe, and one that's global. The global one may be AT&T, for example, if you want. So the global one means it has routers everywhere in the world, it has transocean links to connect them, and if you connect to it from Switzerland, for example, probably you connect to it in Geneva. If you connect to it from Silicon Valley, you connect to it directly in Palo Alto. So it has global presence everywhere, whereas those twos don't have. Right? Now, if you look from the viewpoint of ISP3, who has a customer C3 and has some traffic to send to ISP2 for a customer C2, for example, to destination N2. What should ISP3 do? Well, ISP3 peers with someone else in Europe, for example, through a transatlantic link, a shared cost link here. That shared cost links typically costs a lot. So you pay huge amounts of money to rent or own this link here. And if there's a lot of traffic on it, then you need a big link, so you will pay more. So it might be interesting for this provider to say, oh, but I can connect here in New York City to ISP1 with a cheap connection. ISP1 has global presence, so ISP1 will carry for me the traffic through the ocean and reach ISP2. If I could do that, I could save, in fact, the need to be connected globally. But will ISP1 accept to do that? Probably not. ISP1 says, if I do that for you, in fact, I'm providing you a transit service across the ocean. So you are my customer. So I want you to pay me. If there is no commercial deal between ISP1 and ISP3, where the ISP1 agrees to be transit, then ISP1 will not allow this. So that is the goal of policy routing, is to make sure that the traffic sent by ISP3 to Europe doesn't go through ISP1, but go through mechanisms that ISP1 doesn't care about, but doesn't pay for. For example, here is how this could be implemented. An important part that we have in BGP is the import and export filters. So you will see in the lab how to do access lists to allow or to refuse some things to happen, in particular some BGP updates, some BGP packets to be allowed or not allowed. It's done at the import and at the export. So if we are ISP1, so the big guy in the middle, he might say, for example, I accept, if we zoom at what I accept from ISP2, for example. So ISP1 is peering with ISP2. ISP1 will accept routes from ISP2, for example, that have the path ISP2 C2, because C2 is a customer of ISP2. So ISP3 wants to be able to send traffic to C2 because of it wants to connect to that part of the world. But ISP1 would refuse a route like ISP2, ISP3, C3. So this route that goes across the Atlantic, sent to ISP1 by ISP2, would be refused by ISP1. Or at least ISP1 could write a set of rules that would forbid this. Because ISP1 does not want to use ISP2, ISP3 as transit, which is the over. Now we can say, why does ISP1 not want to do that? Well, that could be for the converse reason. ISP3 was trying to save on the cost of the transocean link by cheating and using someone else's link, but the opposite arguments may be true. If you are a company like Swisscom or AT&T, you have a lot of infrastructure, you sell it at a given price, you want to be sure that customers get the service for the price that they pay. So if you are a Swisscom customer or an AT&T customer and you have traffic that goes from Europe to the US, you want to be sure that it goes with the quality of service that AT&T is able to provide to it. Perhaps AT&T is also using this, is using some kind of traffic segregation for specific classes of traffic. And so it doesn't want to take chances and say, I go here. Yes, it will be cheaper, but it will also be unpredictable quality. So that might be a reason for ISP1 to not accept this. Similarly, ISP1 doesn't want to serve as a transit for the guys that do not pay to ISP1, so it would not export to ISP3, so to ISP3, it will not export a route like ISP2 C2 or ISP1 ISP2 C2. So ISP1 will not say to ISP3 that it has a route to ISP2. Because if it would be doing that, it would be serving as a transit. So ISP1 agrees to see ISP2 and ISP3 as peers, but none of them as customers. So by playing with those import-export rules, this is how policy is implemented. Of course, this is the very tricky part of BGP. We will not see it in detail other than in the lab. In the lab, we will have small BGP networks. You will have to do your rules where it's overseeable. Of course, if you have a large network with peering with a large number of other networks, then this is a significant part of the problem of configuring BGP, is how to set up these rules. And if you do things wrong, you might lose connectivity, which happens once in a while. So this is at a high level how BGP is. Now let's see how, at a lower level, how it works more concretely. So BGP, as we said, uses TCP connections. Now, a big difference with OSPF is that BGP does nothing if there's, sorry, that's not a big difference with OSPF. BGP does nothing if there is no change. That's similar to OSPF. There is no link state update sent except after a very long timeout. But a difference is that the update messages contain only the modifications. With OSPF, the update message contains the new state of everything. In BGP, we send only the delta. So that's why it's called an update. And there is an explicit field in the delta saying whether you are withdrawing or adding a route. The effect is that in steady state, once it has boot and it's synchronized with the neighbors, a BGP router transmits only modifications, and if there is no modification, it transmits nothing. This is highly ideal because in practice there is always something to modify, and we'll see how this can be handled with route flap dampening a bit later. A mental model of a BGP router is it's a pipeline that is working on a stream of messages. So it receives from its neighbors, also from its internal configurations, routes with the paths. It applies the decision process to select the best route, or none, if the policy forbids it. And then it exports the best route to its neighbors. Right? So the key thing is here going from this to this. So it receives a number of routes, and it selects at most one route, which we have seen already on the previous example. It can have multiple routes. It will choose at most one. And what a BGP router says to the rest of the world is always based on what it itself has kept. So even if a BGP router knows there are two routes to a given domain, it will give to the other BGP routers only one route, including internally in the mesh. So this is also very different from OSPF. In OSPF, all routers know of all the possibilities, and they each compute their best path based on all the possibilities. Here, all BGP routers know only of the best choices done by their neighbors, not of all the choices that they had. And as we have seen before, also as only routes learned from EGP are sent to an IBGP neighbor to avoid useless repetition. So this is one model that's often given for a BGP router. We see all the elements. So the elements are first the routes that are obtained locally or redistributed. We'll talk about that in the later. For example, if a BGP router is connected directly to a certain prefix that it needs to advertise to the rest of the world, that will come from local information. But most of the information comes from the other BGP routers, and all information that comes from other BGP routers is stored. It is used by the decision process to keep the best route, but everything that has been received is stored. Why would we do that? What's the benefit of keeping things even if they are not the best ones? Yes? If there is a change of rule or if something breaks, exactly. So if a router here has 3 routes to a given destination, and if keeps one of the 3, but if later the one that it had kept disappears because, for example, this link is down, then this will be detected. There is, of course, a hello message between BGP routers, a hello protocol between BGP routers. So if this route becomes invalid, then there will be a change of status here on the input database called the RIB-in, and then the calculation will be redone with the ones that are still valid. So by remembering all the ones, you can react immediately to changes, which is necessary because, remember, BGP gets as information only the changes. So if one route is deleted, and if you had not remembered the other ones, then you would not know what to do. The BGP decision process will pick one route, and then we'll send it to the neighbors after applying the possibly export rules that might prevent some things to be exported. There might be also here a change of the priority fields or also aggregation, as we will discuss in detail. And here somewhere there is also the routing table that somehow must be involved. I mean, those routes, sooner or later, must be fed into the routing table. We will discuss in detail how this is done. A route in BGP terminology, like in OSPF terminology, is a prefix and a path but also a large number of other attributes. On the animations I've shown before, I was just showing a path like A, B, and 1. So this is contained in the attributes of a route, and all the records that are written in these tables called RIB, routing information bases, at the input, the one that you keep, or at the output, they contain the destination prefix, the AS path, things we've seen before, plus a number of other fields, and we will see a number of them. A field that's very important is the next hop. Without it, BGP doesn't work. And there are things like priority fields that are wait, local pref, or med, that are used to be able to manipulate the choice by giving priorities in some sense. The decision process is the part of BGP that selects the best route. If we compare to OSPF, the decision process in OSPF is Dijkstra's algorithm. We compute the shortest path, and this is how we pick a route. Here, it's different. Here, it's a more qualitative process. It's more intelligent, if you want. We apply a number of criterions, which, in principle, by default, are those ones. So they are chosen, you go in this order. So if you have multiple routes, you evaluate criterion 0. If one of the routes wins, then you stop, and that's the winning route. And you can, if they are equal, or if this is not applicable, you continue until you have something that can be used to make a difference. If we ignore this, the weight is a priority field. This is also a kind of priority field. The first thing we have seen on an example was the shortest AS path. So if you have two routes that have the same weight and local pref fields, then you will pick the one that has the shortest AS path. Right? If they have equal AS path lengths, then you might have other criterions, and we will see examples. This criterion, eBGP is better than iBGP, means if you have two routes that have everything equal, the route that was learned over eBGP, that means you have obtained it from a neighbor that is external, this one will be considered better. So we will see examples of this. So here is what I call the fundamental example, which is a very simple animation showing all the cascade of events that explains how BGP works. So I'm assuming I have two domains, AS, X, and Y, and 4 BGP routers. And inside this domain here, there is well, I don't know what there is exactly. I assume there's only 2 routers, and those 2 routers are constituting a BGP mesh with only 2 of them here. Right? And I'm focusing on this domain here. Right? We focus, in fact, on R1 and show its BGP information. Right? So R1, which is here, receive from R3, which is this router, the information about all the prefixes that are present in the domain Y. I'm using 10 dot something addresses to avoid hurting anybody who would own a specific IP address. But of course, in reality, it's very unlikely that you have 10 dot something addresses with BGP, although it exists in some contexts, but not in the public internet. So in Y, there are 2 prefixes, 10.1/16, 10.2/16. I'm showing here IPv4 because it's shorter to write. In the future, you expect to have more IPv6, and BGP handles both. It works both in the same way. So assume that those 2 routers, R3 and R4, are instructed by configuration to export to the rest of the world those 2 prefixes, even if they are not directly connected, but they are both exported. So R3 has said to R1 over eBGP, I have a route to 10.1 and 10.2, and the AS path is just me. Why? Right? So what will R1 do? Well, it has only one route, so it keeps it, it remembers, and it will keep it as best, because there's no other one, assuming, of course, the policy does not forbid it. So the best route is this one, and there's an attribute, next hop, which is 1112. So the next hop is an IP address that can be used to go to this router that is advertising this here. And this IP address is an IP address of a link between the two domains. And this is the only thing that is shared in BGP. This IP address is considered as internal by both domains. Right? So this link must be considered as internal. What does it mean when I say it's considered as internal? That means that any router in the X cloud must know, through OSPF, for example, how to reach this address, 111.2, even though it's an address of a BGP router in some other domain. And this is called the next hop field, and we will see next week how it is used to provide complete reachability. Thank you very much. See you tomorrow.